Hi, I'm Mike,
I'm Don,
and this is the International Space Station.
Science Garage.
All right, so go ahead.
So this is just a Geiger counter.
It's a Geiger counter. Okay.
So it measures radioactive stuff. So grab your cup of coffee.
All right.
And it is. Oh, look at the meter now.
I don't know what.
So your cup of coffee is radioactive.
It is?
According to this
By how much?
radiac.
Point it up to my head. What do you get on my head? Anything?
Nothing. You're okay.
Look in here. Do you have anything in there?
Nothing in there either.
That's what I figured. That explains a lot.
Okay.
It's a very accurate machine.
So this thing, this cup dates back to the 30s, and this orange glaze is from a uranium-based glaze that they used to use, and the glaze on this cup then is radioactive, which is why the Geiger counter was going off scale high from when you pointed it at this cup. And on space station, we have to worry about radiation. It's a little different than this. It's not radiation from radioactive decay, but it's radiation from galactic cosmic rays.
Okay.
It's radiation from space. There are
Okay.
high energy particles that come zooming down, and since we're out of Earth's atmosphere, we have a higher level of radiation than we do down here on the ground.
Right. Okay, so like the South Atlantic anomaly.
Oh, yes.
Is that the same? It's not the cosmic rays. That's a
You know,
different.
South Atlantic anomaly has cosmic rays and other solar protons and other things.
There's lots of
There's lots
sources.
of stuff.
But so the intergalactic cosmic rays is one issue.
Yes.
All right. So this thing. Do you have something like this? You do have something like
Yeah.
this.
On
don't you?
station, we had a cosmic ray detector.
And that thing you ran on the computer?
Yeah.
That would go off every once in a while.
Yeah. So it would make little clicking sounds
Yeah.
like a Geiger counter, and little lights would blink every
Yeah.
time it measured a cosmic ray. And you
Right.
could set this up, and when you weren't in the South Atlantic anomaly, it would measure at a certain rate. When you went into the South Atlantic anomaly, the rate count would go up by about a factor of 100, maybe even 1,000.
And the reason we have this South Atlantic anomalies, we have radiation belts around our planet.
Yes.
Right. The Van Allen.
Van Allen
radiation.
belt,
And they're held in place by
magnetic fields.
magnetic field, right?
Yeah.
So, and that's where the South Atlantic anomaly is, where the Van Allen belt kind of comes closest to
Yes,
Earth,
it does.
right? So the other parts of this belt, these Van Allen belts, are a little further away, but it
That's
dips
right.
down.
It dips down
that one
over
area.
the South Atlantic anomaly, and astronauts get about 40% of your total radiation dose comes from just the short periods of time that you pass through the South Atlantic anomaly.
Right, and it also is a function of your altitude.
It is a function of
The
your
further you get
altitude.
away,
The
the
worse
worse you
it
are.
is.
So at Hubble, we were a bit higher.
Yeah, Hubble,
It was
you
a lot
got
worse.
that explains a lot of things about you because you did two
That thing
Hubble
didn't
missions.
even go off. Yeah, that's right.
See, and so I'm surprised it didn't detect anything.
I don't know what the equivalent, but Scott Kelly, who's flown on station and also flown on Hubble, I forget what he said. It was like 2 weeks. I heard him in an interview say something about like the 2 weeks he had on his Hubble flight, or the 10 days he had on his Hubble flight, was equivalent to X on station. I don't know exactly what the X was, but they bring us down for a number of reasons to a lower altitude. It's safer radiation-wise and debris-wise to be at a lower altitude than to be at the higher altitude. And then it's things like spacewalking too. That you were getting a bigger dose, and what I did too.
Yeah.
You're getting a bigger dose when you're out doing that.
Right, and they try not to do a spacewalk when your orbital path is going to go through the South Atlantic anomaly. They try to time it.
Right.
They can't always do it that way, but they like
Right.
to do spacewalks when you're going to have minimum radiation for the orbits.
You certainly want to do it when you knew there was going to be a lot of solar activity.
Yeah, you
or
wouldn't.
something like that. You want to do that. So this is a pretty cool device. And what did it say? It said that my coffee was okay.
Yeah, coffee's okay, but the cup isn't.
So if you held this up to this other cup, it wouldn't happen.
No,
Is that what you're
no.
telling me?
Here's your other cup.
Right.
Yeah.
Okay. So we'll hold
Okay,
that.
let me turn
Make
this
sure
on.
that thing is on.
Okay.
So give me a number. What are we reading there?
0.
Okay. Now what are we reading with the 1930 radioactive cup?
Okay.
Whoa! Look at that thing.
It's off scale high.
All right. So this is. I don't know why you still have this around. By the way.
Well, so that we can use it in Science Garage.
Okay. All in the name of science.
And the whole point is radiation comes in many different forms. Sunlight, in some respects, is radiation. But when you say radiation, people usually refer to particles, radioactive particle, particles from events, whether it's generated through radioactive decay, as in the case of the uranium on this cup, or whether it's galactic cosmic rays or particles that come from the sun, because the sun will go burp and out will come a whole bunch of particles, and then they will end up on Earth. They'll spiral on the magnetic field, they make aurora, things like that. And if you happen to be in space during some of these times, you will get higher than normal doses of radiation. And South Atlantic anomaly is one area where the radiation is concentrated, and you fly through it when you're on a spacecraft while you're orbiting Earth.
Right. And all that is measured. We have dosimeters everywhere.
Yeah, we know exactly what your doses are and all of that.
And the dosimeter I wore in space for my flights was this like piece of plastic.
Yeah, well, it's a little plastic tape, but inside has some...
What is it? What's inside of that thing?
I've never opened one up to look.
I find that hard to believe. But what's the principle there? This stuff, the dosimeter, is really just a piece of material.
Yeah.
Okay?
And it gets some kind of damage. I don't know. They used to be film-based, but I don't think they're film-based anymore.
It seems like they actually work, though, because it just seemed like a piece of plastic they made you. I thought it was just for
but that's a
fun
good question. I do not know how the modern ones work.
We finally stumped Don. Did you have the same thing, though? You had that?
Yeah, except my badge got lost. Somehow it got lost. So.
But that you were supposed to wear that.
I wear my radiation badge all the time that I've been on space.
Right.
Because you want to know what dose you actually have. You don't want to bury it in the bags of water.
It's a little piece of material. It looks like
it's a little plastic thing like that.
Or something.
Yeah.
Is what it looks like.
Yeah.
And you start with it in your launch suit.
Yes.
You transfer it to your in-flight garments, which means your clothes. When you always have it on in your pocket.
Yes.
You sleep with it. You're supposed to be in your pajamas.
Right? Religiously.
Yeah, always was. And when you go out for a spacewalk, you put it inside.
It's just like your teddy bear. It's like your orbit equivalent of a teddy bear.
That's a nice way to put it. You're never without it.